I'd like to do a few Riemann sum examples because this is really what's important for the definite integral. In fact, the definite integral, by definition, is a limit of Riemann sums, but also the reason why definite integrals come up in so many applications is because of the Riemann sum. And we will see this. But here's an application where we can approximate work using a Riemann sum. This is when we have variable force, and this is my force function, and we are told that, well, say the object's moving on an interval 0 to 1. We're also given a partition to use and a sample set. Now, another way that you could say this, we want a Riemann sum here for this function, but you notice looking at the sample set, these are the points, so we were calculating a right Riemann sum by looking at these points. And then here you notice we have 1, 2, 3, 4 subintervals, and they all have equal length. So all of these have length. This delta xi, so in this case, we have a constant delta x. So we have equal subintervals, which is 1 over 4. Or we also discussed this is b minus a over 4, right, with 4 subintervals. Okay, now let's begin. Well, what we need is to calculate a bunch of function values, multiply each by delta x, add everything up. So we will start with our function values. So we are told the points to use. We have S1 is a fourth, and when we take f of S1, this is a fourth squared. We have S2 is, I'm going to write it as 2/4. F of S2 is 2/4 squared. I'm purposefully leaving these all over 16 so that when I add, I already have my common denominator. And then S3 is 3/4. F of S3 is 9 over 16. And finally, S4 is 4 over 4. F of S4, 16 over 16. Okay, now let's do our Riemann sum. So the sum, this is my side work here. I equals 1 to 4. We have f of si, and then we have this constant, all equal length subintervals. Delta x is 1/4. So this is 1/16 times a fourth plus 4 over 16 times a fourth plus 9 over 16 times a fourth plus 16 over 16 times a fourth. And maybe now you see why I kept everything over 16, because now I have everything over 64. And I have 1 plus 4 plus 9 plus 16, which adds to, this is 20 and 30. We get 30 over 64, or 15 over 32. And, you know, as a comment, since we are doing work here, if we're working with metric units, this would have units joules or Newton meters. The force function would have units newtons, and each of these little delta xi's would be in meters. Altogether, we have Newton meters or joules. And this is an approximation for the work. Here is another Riemann sum. We want to estimate this definite integral using a left Riemann sum with the following partition. Okay, now if you see here, this is 1, 2, 3, 4 subintervals, and I have sketched them here, including the rectangles. You will notice with this example, we do not have equal length subintervals. If we did, you know, this length is 1. If we had 4 of equal length, they would all be a fourth, and they are not in this case. So here, the area of these, this is a height 0 rectangle, but the area of these rectangles will approximate this, or be our estimation of this. And this is what we're trying to calculate. Okay, so here we go. Well, With a left Riemann sum, you see our sample points are this point, this point, this point, and this point, and I've already sketched the height, but let's calculate it. So we are going to have S1, S2, S3, and S4. S1 is 0, left Riemann sum, and you know the square root of 0, 0. S2 is 1/4, the square root of 1 over 4. This is 1/2. S3 is 1/3. I will just 1 over the square root of 3. Perhaps I will leave it like this for the moment. And finally, maybe I will move this down a little. S4 is, S1, yeah, okay, very good, 3/4. This is our last one, and the square root of 3/4 is going to be the square root of 3 over 2, like this. Okay, so these are our function values, and now we need to calculate our sum. So I can put a box around all of this. What I need is the sum, I equals 1 to 4 of, it's going to be the square root of SI. This we have calculated, and then times, well, it's going to be delta XI. Unlike in the last case, this is not fixed, as I mentioned. Okay, so we have 0 times, well, it will be 1/4 minus 0 plus the next one, 1/2 times 1/3 minus 1/4 plus, we have 1 over the square root of 3 times, this is going to be 3/4 minus 1/3. And then finally, the square root of 3 over 2 times 1 minus 3/4. This is our Riemann sum. Okay, now comes common denominators, fractions, things like this. This first term, this is the easiest one, 0. Times anything, 0. This one is 1/2. And if you get a, maybe I will do it above, common denominator here, you see it would be 12. And we have 4 over 12 minus 3 over 12 here. This gives me 1 over 12. Then we have a plus 1 over the square root of 3 times. Again, if we do our common denominator, this is going to be a 9 over 12 minus 4 over 12. Okay, this will be 5 over 12. And then finally, we have a plus the square root of 3 over 2 times, well, this is a 1/4. What can we do to this? Well, not really a lot. At this point, maybe we get out our calculator, because this is 1 over 24 plus the square root of 3 over 8 plus 5 over the square root of 3 times 12. This is not going to wind up being a nice fraction anyways because of our square roots of 3. So I would use your calculator at this point, and let's see what we get. Approximately 0.4987. This would be our estimate to this integral using this Riemann sum.